Hi, everyone. Can you all see the whiteboard? What answers did you get for the first question? Good. 100 plus 75 pi is right. Ishan, can you explain?
Yeah, so I just do a diagram of a square, a circle, centered at one of the vertices of the square. So that means the radius has to be 10. So the area of the circle will be 100 pi. So you have to find the 3/4 of the circle. So 100 times 3/4 is 75. So you get 75 pi plus the area of the square, and 10 times, and you know this one side of the square is 10, so 10 times 10 is 100. So it's 75 pi plus 100.
Good. Yep. Let me fix this diagram. So the key points here, it's pretty clear once you have a diagram. So what we want to do here is take the union of the area of the circle and the square. We know that the circle is centered at this vertex of the square. And if this has radius 10, then the area of the circle will be 100 pi, pi r squared. But we only want 3/4 of the circle because we don't want to include this quarter of the circle. We want to include this portion of the circle plus then the square. So because the square covers this quarter of the triangle, this quarter of the circle, we can just include the square here and 3/4 of the circle. So the circle area is 100 pi. The 3/4 of that is 75 pi, and the square is 100. So the overall area is 100 plus 75 pi. Any questions on this? Okay, let's move on to the second question. Okay, good. 18 is right. Nidhi or Neil, can you explain?
So what I did is I kind of used elimination for this, so we can eliminate the possibilities of basically the first digit of, we know this has to be a 2-digit number. Mm-hmm. So you can work on finding J's first, and so it's 2 digits and AB. So yeah, AB. The A has to be bigger than B when you flip it, and it's multiplied by 2. It will, the BA would be greater, but we want AB to be greater. So for example, you would want numbers like 21, 31, things like that. So when you flip it, it'll become 13. Afterwards, you can eliminate the possibilities of anything ending with a 0, because those numbers would be impossible to be greater than 2. So now you're left, and it can't be greater, a number that's 40 or above, because then that would be 2 left. So you're left with a few possibilities, 21 or 31. And I just hand checked those, and I got 31 and 13. And when you add 5 to both of them, you get 36 and 18. 18 times 2 is 36. So I just did 31 minus 13 is 18.
Good. Yeah, so this works. You can kind of start with some values and kind of see what can fit and not. And then, yep, 31 and 13 does work here. In 5 years, 36 and 18 can be the 2 ages. So the current difference would be 18. Did anyone do it any other ways?
Yeah. So you can have like AB equals 31,
Mhm.
and you can have like BA equal to 13.
Mhm.
So since A is in the tens digit, we do like 10A plus B is equal to 31.
Mhm.
And then for BA, we do 10B plus A equals 13.
Mhm.
So then we just do some algebra now. So we're looking at it after 5 years, we can do 10A plus B plus 5 is equal to 2 times 10B plus A plus 5. And then once you combine like terms, you get 8A minus 19B is equal to negative 5. And then you can simplify. What I did was I brought 8A plus 5 is equal to 19B. And then I just plugged in numbers after that. And I think A has to be less than 4, otherwise it's not possible. And then I got A equals 3 and B equals 1. Oh, I think it's supposed to be positive 5 and negative 5, actually.
Sorry. Yep. Okay. Good. 3b equals 1. Good. Yep. So this is a more algebraic way of solving it. So you can write this equation. The nice thing is when AB is a 2-digit number, you can always write that as 10A plus B. And the reverse is 10B plus A, right? And once you know that, you can just imagine once you have variables for Jack's age and Bill's age, you can write this equation, right? So 10A plus B is Jack's age. Jack's age in 5 years is 10A plus B plus 5 is equal to twice Bill's age after 5 years. So Bill's age is 10B plus A plus 5 in 5 years from now. Twice that should be equal to Jack's age, and solving this gives us this relation: 8A minus 19B is equal to 5. And the kind of the important piece here is that we need this to have integer solutions, right? A and B have to be integers here, and we'll see if you just put B as 1 here, we get an integer for A. And we wouldn't be able to find other integer solutions here. So there's just a couple of other things to note here that are sometimes useful. So when I take two numbers that have their digits reversed, so 12, 21, 13, 31, and so on, or any kind of pair of two-digit numbers with the digits reversed, what do we know about their difference always?
Multiples of 9.
Good. So this is pretty easy to see if you look at, like Pavan said, A, B, and BA. You can do this as 10A plus B, 10B plus A. And if you take the difference between these two, you'll get 9A minus 9B, or vice versa, depending on which you subtract from which. And this will always have a difference being a multiple of 9. So in this case, you can use this to see that, so you know the difference between these two ages has to be a multiple of 9. And then in 5 years, they have to be, the difference of the ages still remains the same, right? So Jack will be twice as old as Bill, so you know those will all be multiples of 9. And then if you just try a couple multiples of 9, you'll see that, so when Jack is 18 then, Bill would be 36. And then going back 5 years, you want to make sure that they're actually reverse digits. So 18 minus 5 gives you 13. 36 minus 5 gives you 31. This is another way. So we know that the difference has to be a multiple of 9. We know then Bill minus Jack's age is a multiple of 9. Or sorry, Jack minus Bill's age is a multiple of 9. But we also know that in 5 years, Jack's age is twice Bill's age. So then you basically need to take a multiple of 9 and twice that multiple. So for instance, if we tried 9 and 18, this wouldn't work because 5 years before that, this would be 4 and 13. So this wouldn't be reverse digits of each other. But the next one just works. 18 and 36, you can subtract 5 and see that this works. Any questions on this? So just a general trick that's useful is that when you have numbers that are reverse each other, or you could even use this trick for 3-digit numbers which are reverse, you can write a number AB with first digit A, second digit B as 10 times A plus B. And then you can kind of use it as a variable, potentially to express other constraints or equations. So similar for 3-digit or so on, you could write a number ABC as 100A plus 10B plus C. And potentially, if you needed something with its reverse, you can write CBA as 100C plus 10B plus A. Any questions on this? Okay, let's move on to the last question. Any answers for this question? Good, 25 over 91. Pawan, can you explain?
Okay, yeah. So it's asking if Carol will get a 6. So if the first person doesn't get a 6, there's a 5 to 6 chance they do not get a 6. Then the next person has 5 out of 6, and then she has 1 out of 6. That's one possibility. But we also realize that like it can continue going forever, like 5 over 6 times 5 over 6, going like multiple times. So we just have to find the sum of the infinite geometric sequence. So since there's no really first term, we can use the last term, which is the set of 5 over 6 times 5 over 6 times 1 over 6. So that's 25 over 216. And then we just we do that divided by 1 minus 125 over 216, because that's we're doing like each term as each set of 3 people going at once.
Mhm.
So once you just solve 25 over 216 over 1 minus 125 over 216, you get 25 over 91.
Good. Yep, this is correct. So let's go over this a little more detail. So we have the sequence, right? So Alice, Bob, Carol, and so on. And then Alice, Bob, Carol, and so on. They're each going to roll the die and see if they get a 6. So let's just first think about what's the probability that Alice rolls a 6. That would just be 1/6 probability that she rolls a 6, and the thing would end, right? She'd be the first one to toss a 6. We don't want that to happen, right? So we want Alice to roll not a 6. So the probability of that is just 5/6, right? Now, what do we want Bob to do? So we want Carol to be the first one to toss a 6, right? So we want Bob to also not toss a 6. There's a 5/6 probability of that. And then we can make Carol toss the 6. And the probability of that is 1/6. So imagine if they just did this process once and ended there, then the probability that Carol is the first one to toss a 6 is just 5/6 times 5/6 times 1/6. If it was just that, it was easy. But the problem is that they repeat again, right? So if one of these 3 rolled the 6, the game would have ended, or we wouldn't have more things to count. But there's this case where what if all of them didn't roll a 6? And the probability of that is 5/6 times 5/6 times 5/6 is that they all didn't roll a 6, right? And then this whole thing is going to repeat again. So after Alice, Bob, Carol, now again it'll be Alice, Bob, Carol. Now, so what if none of them rolled a 6 the first time that each of them went, and the second time, then Carol rolls the 6. So then again, she would still be the first one to toss a 6. The probability of that is now, the next time Alice rolls, again, it's 5/6 probability she doesn't roll a 6. 5/6 probability Bob doesn't roll a 6. And then 1/6 probability that Carol rolls the 6. So this is if it happens for Carol the second time. But now we can repeat this again, right? And say that maybe no one rolled the 6 in the first 2 rounds, okay. Okay, so the next step is kind of if no one rolls a 6 in the first 2 rounds, and then in the third round, Carol rolls her 6. So that'll look like this with another 5 6 again for the first round. So again, 5 6 probabilities for the first 2 rounds. These first 6 terms here are all 5 6. In the last round, should have 1 extra. 2 5 6. So Alice rolls not a 6, Bob rolls not a 6, and then Carol rolls the 6. So are we seeing a pattern here now? So every time it's like 5 6 times 5 6 times 1 6. Then we put 3 5 6 first, corresponding to none of them roll a 6, and then the same 5 6 times 5 6 times 1 6, and so on. And this process will actually never really end because this could go 10 rounds, it could go 100 rounds, but all of them need to be counted. So this is something that's called an infinite geometric series. So you've probably seen an arithmetic series over a geometric series. Arithmetic series increase by the same amount. If I say 1, 2, 3, 4, so on, these are increasing by 1 each time, or 2, 4, 6, 8, or 1, 5, 9, 13, so on. These are arithmetic series. Geometric are ones that have a common ratio. So I'm multiplying by the same number each time, 1, 2, 4, 8, 16, multiplying by 2 each time. So if I try to add up the values here, this would just become infinity, right? It keeps growing larger and larger. The interesting thing is if the ratio is smaller than 1, if I take the values 1, 1/2, 1/4, so on, these values actually sum to something that's I can actually compute the exact sum of this when I take 1 plus 1/2 plus 1/4 plus so on. And the kind of intuitively you can think about it is that in the first case, the numbers are getting bigger and bigger, right? So as I'm adding, if I've added some number of numbers, the next one is even larger, and this will keep growing larger and larger. In this case, the numbers become smaller and smaller when I go in. So towards the end, they're not increasing it by much, and I can actually compute what exactly this equates. And it's actually neat to see how you can actually compute this. So let's say this is equal to sum A. Let's now multiply this by 1/2. So what do you get? 1/2 plus 1/4 plus 1/8 plus so on is equal to 1/2 A. Does anyone have an idea how to solve for A given these two equations?
Is A 2?
Good, yep, it is 2. So how do you get that from these two?
So for the second equation, you have the 1/2 plus 1/4 plus 1/8 and so on. And in the first equation, you have that exact same sequence, but except you're adding an extra 1. So the difference between A and 1/2 A is half of an A. And so if half of an A is equal to 1, then A will be equal to 2.
Perfect, yep. So in this case, you can see that all the terms here are the same after the 1/2, right? So let me use the pointer. The 1/2, 1/4, 1/8, and so on. As this goes on and on and on, this part is the same between these two. The only difference is this has an extra 1, right? So what we can say is 1/2 A plus 1 is equal to A, and then you can solve that it's actually 2. So imagine if you take 1 plus 1/2 plus 1/4 plus 1/8 and so on, and repeat this, you actually get 2 in total when you do this. So we could actually apply exactly the same logic here. We want to add up this probability, plus this probability, plus this probability, plus so on. The first being Carol rolls her 6 the first time, the second time, the third time, and so on. So let's actually do that here. So what is the first probability here? Pavan told us this was 25 over 2/16. If you multiply 5 6 times 5 6 times 1/6. Now the second time, it's 25 over 2/16 is the last part, times the first part is 125 over 2/16. And the third time is equal to 25 over 2/16, corresponding to the last three, times 125 over 2/16, times another 125 over 2/16. So where these three terms correspond to 125 over 2/16, these three are 125 over 2/16, and the last one is 25 over 2/16. So now what is the sequence that we're trying to sum? It's 25 over 2/16 plus 25 over 2/16 times 125 over 2/16 plus 25 over 2/16 times 125 over 2/16 squared, and so on. So can we use the same kind of trick we did with the 1/1/2 to actually compute this sum? Any ideas? So what did we do for this 1/1/2 case? What did I multiply it by first? Any ideas? 2/16, we can try 2/16. Let's see. So let's, the 2/16 actually might help to better see what's going on. But let me show you if we actually just multiply by 125 by 2/16. So what we really generally want to do is multiply by the ratio. So what is each term, from the first term to the second term, what are we multiplying it by? 125 over 2/16. From the second term to the third term, we're again multiplying it by 125 over 2/16. So if we multiply the whole thing by 125 over 2/16, what we get is, now the first term becomes 125 over 2/16 times this, then this becomes this squared, this cubed, and so on, is equal to 125 over 2/16. Now, how do the terms match up? Can we see a similar pattern here? So this term is the same as this term. This term is the same as this term, and so on. So the only extra one is this, right? So we can write a similar equation as 125 over 2/16a plus 25 over 2/16 is equal to a. Now if we solve for a, we can subtract this 125 over 2/16a from the other side. So we'll get 25 over 2/16 is equal to 91 over 2/16a. And you can solve this and get a is equal to 25 over 91. So the same thing, to make it a little bit easier, there's a formula that says when I take a is the first term, a times r plus a times r squared plus a times r cubed plus so on up to infinity. Assuming that r is less than 1, we already saw that if r is greater than 1, it becomes like this 1, 2, 4, 8. Everything just grows larger and larger. We can't actually add that up. If this is true, then this sum is actually equal to a divided by 1 minus r. This is what Pavan used, knowing that the starting term is 25 over 2/16. This ratio is 125 over 2/6. You can just plug it in and solve for this. But this is actually the same thing that we did here. It's just a more concise version of this. Any questions on this? So this formula at the end here is the sum of an infinite geometric sequence. And it's useful to know, especially with these kind of probabilities, when an event could happen the first time, second time, so on, without a limit to that, you can add up these probabilities easily using this formula. Any questions on this? Okay, that's it for today's class. We'll see you all in 2 weeks.